Okay, so here's a problem. We have a cantilever beam with a 5-kip load in the middle. We have values for E and I, and we want to know the slope and displacement at B. So I think this would be a good problem for conjugate beam, so let's try that. So if we're going to do conjugate beam, the first thing we're going to need to know is the moment. So I'm going to shortcut it just a little bit and tell you that the reaction at A is 5 kips and that the moment is 75 kip feet. I think you could probably find those. It's pretty easy. You can just see the only force in the system balances, and this moment should balance the 5 kip times 15, which I think is 75. There is no axial force. So I'm going to go ahead and quickly sketch my template for my shear moment diagram. So there's my positive X, my positive shear. These will all have values of kips. So the shear at A is 5. The change in shear is equal to the area of the load curve, which is 0, so it's going to stay 5. The slope of the shear diagram is equal to the load. The load is 0, so the slope is 0. As I go from the left side to the right side of this 5 kip force, I come back to 0, and then there's no load. So we're done. There's the shear diagram. The moment diagram, there's my positive X, positive moment. All these values will have units of kip feet. I'm going to start with a bending moment of minus 75. Again, the change in moment is the area of the shear diagram. The area of the shear diagram is a rectangle, 15 feet by 5 kips, so that's positive 75, which brings me to 0. The slope of the moment diagram is the value of the shear. The shear is constant, so we have a constant slope, and it's positive 5. So there's my moment diagram. So my moment is negative, so when I apply it as load to my conjugate beam, I'll apply it as a negative load. So what's my conjugate beam look like? Recall how our conditions change. So a fixed end, when mapped to the conjugate space, becomes a free end, and the free end becomes fixed. So it looks like the structure turns around, and on that beam I'm going to apply this. What I like to do is just put it over there. Just map it right over. There's the moment diagram on it. It's going to have a value of 75 over EI. And remember, the units of the numerator are kip feet. So this is a negative moment. So what's negative load? Up or down? Down. And let's just not forget that this is 15 feet and 15 feet. Okay, so there's my conjugate beam. It's got the proper load on it. Now the problem asks for the slope and displacement at B, and this is B. So displacement in the real beam is what in the virtual beam? Moment. Slope in the real beam is what in the virtual beam? Shear. So all I have to do is go to B and assume a positive bending moment at B and a positive shear at B. Right? And I just have to solve for those two things. So if I come over here, I should get a concentrated equivalent force. I'll just call it F. And what will that be equal to? The area of the triangle, which is 1/2 base, which is 15, times height, which is 75 kip feet over EI. So what's that equal to? Somebody will have to help me with that. That would require a calculator and your fingers. 562.5? So that's going to be kip feet squared over EI. Now, what's going to be the distance from the right-hand side?
25.
We know this is 15 feet, and then 2/3 the distance is 10, so that's a total of 25. So I have everything I need. So now I'm going to come and sum moments at B. Make sure it's in equilibrium. So summing moments at B, I've got a positive moment at B. And then my concentrated equivalent force is also creating positive moments. So that would be 562.5 kip feet squared over EI times a moment arm of 25 feet and nothing. So my moment at B looks like it's just going to be the negative of that. What's that equal to?
$14,062.5.
14,062?
Yes, sir. 0.5 over EI.
And that's going to be kip feet cubed. So if I now convert that, because I have values of E and I, so E is 30,000 kips per inch squared, and I is 800 inches to the fourth, and I convert cubic feet to cubic inches. I should get some value that is negative. I'm thinking it's pretty close to 1.
1.0125.
1.01. That's close enough for me. And it's negative, which means it is up or down? Down. Does it make sense that B goes down?
Yes.
I think it does.
That's displacement?
That's displacement. So now we can find the shear by summing forces in the y direction. In this case, I have my shear force acting down and my concentrated equivalent force is acting down of 562.5 kip feet squared over EI. So you can see it's pretty easy to solve for my shear. The shear at B is negative 562.5 kip feet squared over EI. So what is that? So it looks like we're going to have a negative slope, which seems to make sense. And now we just need to divide it by E and I to get the number. So again, E is 30,000 kips per inch squared. I is 800 inches to the fourth. And convert cubic feet to square feet to square inches. This is going to be a pretty small number, I think. Yeah, pretty small number. What'd you guys get?
0.00337.
0037. That's pretty close. That's close. 373?
337.
Oh, 337. And that'll be in radians. Pretty small angle. It also came out negative. I lost my negative. But that makes sense to me because this beam should displace something like that, and you can see that you have negative displacement and the slope is negative. That seems to match up pretty good. So any questions about that? It took about 10 minutes to do for me, or for us. So I think it's a reasonable problem. Not that you would get one like this on an exam, but
It's a very good test question.
oh, you like that as a test problem.
It has the right amount of challenges.
So if you see...
I'll stop the video now before I say something that I don't want to record.